I'm Anthony Lamping. This is Austin. At the end, we have Nick and Justin. We're part of the University of Cincinnati UAV Master Lab. All of us are aerospace engineering students. On the ends are undergrads. Him and I are graduate students.
Take it away. Awesome. So just a little bit of overview, kind of some of the things we'll go through today. Since we only have 10 minutes, we're going to try and keep it nice and concise. There's a lot of stuff here, so we could have been here for an hour going through a bunch of slides. So we're just going to try and keep it concise. Any questions you guys have at the end, it'll be easier to just answer them that way. Basic, honestly, I don't want to, everybody's familiar with the problem statement here. Obviously, we're taking advantage of the OSGC competition here to see what kind of endurance we have in our VTOL platforms. So these are not, we're not necessarily being super novel, like the team before was being highly novel in their anticipation. We're kind of using the things that we know work and trying to kind of fit those bills to kind of meet this, this competition. So we're basically going through VTOL using small UAS systems to kind of meet some endurance clause here. Really, where a lot of this stuff lingers is from design studies for drone optimization platforms. So everybody's familiar with quads, and that's kind of the easy pick of the litter is a quad rotor. A hex or an octo are very similar. So you'll see a lot of these platforms over here in use for high-end professional-based platforms. The idea is fault tolerance, right? So you can have a motor go out and it's still more of a stable platform than it would be over here. However, if you look at the aerodynamics, you look at the efficiencies involved in such systems, what happens is when you increase the amount of disks that you're going to take up this one bit of disk area, if you call this disk area, if you increase the amount of disks that you have, right, the disk area individually gets smaller, right? So there's a maximum disk area that you can actually have and still be efficient. So what we were interested in doing is finding out what the most optimum setup would be. Turns out, a quad that's stacked, kind of as you see it here with motors top and bottom, is actually the most efficient setup. It provides some pretty serious fault tolerance, which we'll talk about here in a second, because we sadly found that out. But ideally, it provides optimal efficiency, and you don't have to worry about, additional arms, additional components to attach the arms, additional motor mounts. You're utilizing the same componentry you have for 4 motors, but you're adding 4 more motors for free on the bottom side. So again, there's a lot of stuff between there and here, so we're just going to kind of try to keep it brief and we can answer any questions that go by. This was basically the competition platform that we decided to build. We called it Hefty. It was a coax. It uses actually the same motors the previous team was talking about using on the last performance. So this is a U5 KV400 motor up top and an anti-gravity motor down low. These are both made by T-Motors. The big difference is both of these operate on 6S. The motor up top produces about 4,000 grams of thrust. The motor down low produces about 2,500. The reason that we offset them that way is because according to Glauert's theory or momentum theory, if any of you guys are aerodynamicists, obviously you have a propeller above and a propeller below. They're not going to contribute 100% the same way. So we actually built some thrust stands. We actually took some thrust measurements and kind of figured out what that staggering was, what the maximum efficiency was. And we designed our platforms around that value. What we found out was the motor below in this downwash region is about 70% as efficient as the motor above. So you can kind of always keep that into account. So what we did with this platform that we didn't do in previous platforms is we staggered the motors. We put a much more powerful motor up top, something more efficiency-based down low, and that seemed to make a little bit more sense. We weren't eating the weight of the heavier motor down low when we knew we weren't going to be producing the thrust since it was in the downwash region. Some of the specifications based on this platform itself, we just kind of list through some of the pieces. It was all built out of 3.3 millimeter carbon plate. It used 6000 series aluminum mounts and standards. Everything on here was actually built off the shelf. So motor mounts, arm mounts, everything you could buy. What we built was the plates. So we took, using CAD, we built some custom plates, ordered some carbon fiber plating, and then just manufactured them ourselves. We've got some extensive work using Hex and Taro platforms, and we kind of determined that manufacturing things to fit our needs makes way more sense than trying to build things off the shelf. So this specific platform is what we built for the competition. Ran on 6S, 20 amp hour battery, would hover and fly for around 30 minutes or so of competition flight time. What happened during testing is we actually ended up having a bad batch of motors. So what you'll notice is that this motor and this motor are the same. That happened through testing. So we actually had almost a fire on the front corner motor here. We actually were testing, and it looked like, if anybody's familiar with show planes, it looked like we were shooting smoke out. And our remote pilot turned the smoke on, and all of a sudden the craft is smoking, and we're all like, that's not right. Interestingly enough, the craft was about 65 feet in the air and stayed there. So we have an upper motor producing about 20% of the thrust for the whole craft, and the craft stayed stationary in the sky like nothing happened. So what that goes to show is that the fault tolerance involved in a stacked coax is actually really good, considering the thrust efficiencies of the top and bottom motor. So we really proved a fault tolerance, even though we weren't out to prove a fault tolerance whatsoever. So with that said, what we ended up doing, since we were kind of chasing the manufacturer, we went back and rolled up back to a previous platform which we had used, which we call mini heave, which is to the right. So this is actually the platform we're going to be flying due to the component failures we had here. They're pretty much very much the same. The hefty platform that you see that's a little bit bigger was just kind of a scale up. It was designed to fly a little bit longer, carry a little bit more. But effectively the same lessons which were learned in the small one were applied to the large one. So control-wise, parameter-wise, everything pretty much seemed to be the same. But just in case everyone was wondering, this is kind of the setup. However, what you'll notice is, based on our values, the smaller one actually flies a little bit longer, and obviously that's because of the weight. So its platform weight is a little bit, it's about 600 grams lighter than this one naked. And then you add up the components, it ends up being about a kilogram, so that all adds up to flight weight.
All right, so here, talking about the competition-specific requirements, we had to have a payload bay on the vehicle. We designed a small wooden box to carry the payload, and you can see right here the side and the bottom both open up so that we can easily insert the payload as well as take the payload out, as well as mount the box. It was laser cut from basswood, and as per the requirements, it is not a structural component of the vehicle, and it completely encloses the payload, and it lies right on the CG, so we can fly with or without this payload.
Correct.
All right, so I have 2 minutes to talk 8 slides. All right, so FlyMaster is a software system that I developed. It's based on ROS, and it communicates Mavic ROS 2, PX4, in order to create this easy system for everybody in the lab to use to actually take UAV flight in the air. So there's always a bunch of people working on algorithms for obstacle avoidance or a bunch of stuff. So this software was a means to reduce all this controls burden that everybody has when they try to fly these things. So it's defined an easy interface that doesn't rely on the actively changing interfaces of all this open source software system. And that is the basis for a lot of this. So it's huge on platform flexibility. Different programming languages are supported through ROS. It takes care of all the driver integration, message passing, distributed networks, so you can have multiple of these things in the air at the same time, which we've done before. And we created this simple ground station interface that really doesn't rely on the link, so the link can die. All this stuff mostly runs on the onboard computer on there. So as you can see in the picture right here, we have this is ground control.
1 minute. Sorry, 1 minute.
Okay. This runs, all right. Okay. Pretty much settled that. ROS has been growing over the years and pretty popular for doing something like this in research. PX4, they already talked about it, supports everything from Pixhawk hardware to Intel Aero. Does all your state estimation for you, so you don't have to dig into the dirty details of that. And you can have consistent execution and software in loop testing, which is key for evaluating your algorithms. For this, we take off, we fly the starting position, which is one of the 2 endpoints, whichever's closer. We have a battery monitor that does this, that constantly watches it while it flies, and then it'll determine if it should land or complete the next lap on its own. and then when it's low enough, it'll fly back to where it took off and land all on its own. So we just hit enter, and it goes, does all this, comes back. Some screenshots of this, doing this in testing. You can see here, it launches, so it converts everything to ANU coordinates for the flight controller. Flies the course, tells you some nice things, number of laps, all that good stuff. And then I quick interjected and just sent a little battery signal for fun, and it went into landing all on its own. Any questions?
So I guess before we hit that, I think the mission of, so our mission here for this competition is to fly VTOL SUAS in out and back, so point-to-point laps, autonomously through a ground station with no remote pilot intervention. So to summarize what we're looking to do, that's basically, I guess, the summation. So, questions?
What speed do you estimate this aircraft flies at?
Exactly 10 meters a second forward and backwards, minus transitional states.
Plus or minus
wind speed.
0.1
plus
meters
or minus
per second.
1 meter per second.
Yeah. So we tested a slew of different flight speeds to maximize
Distance.
Yeah, because there's a relationship between speed and distance, and obviously since we're not going a straight line and we have to turn to go back and forth, we waste a lot of power when we do this.
It's more of an optimization of power consumption,
Yeah.
right? So what forward speed and what transitional speeds and what transitional control laws give us the most beneficial or efficient?
Yeah, and to test this, we flew a series of different speeds and then kind of settled on one that gave us the best performance.
And honestly, it could have been optimized even better, but we did a decent amount of flight tests to know, but yeah, it could obviously be further out.
Yeah, for this competition alone, we probably flew a vehicle in the air. The vehicle was probably in the air for probably, I'd want to say 5 hours.
5 hours of flight time, specifically for this competition.
Yeah.
So can you translate meters per second to miles per hour?
Google can.
Yeah,
pretty
Google
well.
can do that for me.
Yeah.
I have a standard
Do you have an
statement that
estimate?
pull it up because I'll ruin it.
22.369.
Yeah.
So if you got a half an hour flight time, you could fly 11 miles.
Yeah, we're looking at about 25 kilometers. So yeah,
Yes,
roughly.
yes.
About the same.
It was 12 miles.
Yeah.
I think is what we flew last time we flew, and we had more that we could fly.
So yeah, and
We were being a little conservative.
we're being
on
conservative
battery.
with the battery. So tomorrow we're going to be having a battery that's a little bit more juiced, a little bit more charged,
It's
and we're
a
going
brand new
to be
battery.
degrading it down past the point that we normally would. So we actually have one battery that hasn't been used. So we're going to put it in. It's going to be brand new, and hopefully it'll give us the peak performance, right? So it won't have any degraded states. It won't have any recharge states. So it'll just be a pure battery, pure performance. So
If you were going a straight 50 miles, how far do you think you would go?
that's an interesting question. I would say 15 to 16 miles based on what we've seen. So it's efficient forward, right? Obviously with the wind, if I wish we had some time to go through some of the data, but if we would have looked through that plot that he showed you on the side, what he actually set up was we had a lap that we would call. We had a leg, and we could actually look at the consumption. We could look at the power consumption by leg. And so some legs, and these legs were 230 meters long, so roughly almost the length that we'd be flying at the competition. We're consuming a couple of percent off the battery. So we're almost consuming as much stopping and turning as we are just going out and back, so to speak. So going straight, yeah, I mean, and when I say 15 miles, that might be underestimated. I mean, it might be double. Because we don't know. I mean, and I don't really know how we'd be able to test that. I don't know where we'd be able to go around here. We have access to Wilmington. We can get some COAs, but that's only going to be a mile or two. So I'm not certain where we'd be able to go to actually test that and keep line of sight, with all the restrictions.
In order to kind of alleviate some of this, we played with a few different algorithms. So so we have these 2 points that are given by the 2 poles when we get out there. We played with creating an ellipse around this and doing a more coordinated turn flight. We also made a capsule, so you're not wasting time going out here. And we didn't see any gains. So we determined, and I sent an email and said, can we just fly point to point? Because we're, either way, the way force works and the way these things work, is it didn't make any sense to do that.
There's no reason to turn left and right when we're
There's no
just trying
reason
to go forward and back.
And it's easier this way, actually, for safety's sake, for remote pilot takeover, because we're maintaining the exact same heading the whole time as it goes back and forth. So if he has to take over, he knows exactly the way the craft is oriented, which is kind of a difficult thing when you fly these things very far away from your line of sight.
Right. So if we can imagine this thing a ninth of a mile, you know what I mean, a sixth of a mile away, 200 feet in the air.
You might be able to see the landing gear.
Yeah,
Right.
you don't really know which way it's facing, so knowing the heading is kind of a big thing when it comes to safety.
Yeah.
So that was also a big consideration in trying to maintain that. And instead of flying, so we're not flying simple mission waypoints here that you can do in ground control or anything like that. We're flying in an off-board position mode where the onboard computer is constantly sending these position commands.
Right. And so we'll have a ground station. We'll have a battery parcel unit that we'll be powering our own setup with. And if at any moment, once the mission started, we could actually unplug all of these pipes that are communicating in the craft, would actually continue exactly on its course and fly until the battery estimator said, hey, the battery is too low and it's been too low for too long, come home.
Yeah.
So it's, again, it's designed to be, you hit the button and watch it kind of thing.
Now, you came up with this 10 meters per second
Yep.
speed. Now, is that kind of the best speed for going the most distance?
Yes. So that's the optimal speed for which we can travel the furthest distance.
In
So
this
since
particular
in this
competition
particular
where we're turning.
correct.
every
With this
sixth of a
particular
mile.
set of maneuvering,
Right.
that happens to be our best speed, accounting for a hard pitch and then a transition back, and obviously the subsequent altitude deviations that you get through the Pixhawk and through just those kind of multi-coupling controllers, that just happen to be through our testing the best.
Yeah, it sounds like a nice round number, but we actually tested a bunch of weird
we
numbers
tested
around.
every number between 6 and 12. It seemed like.
Yeah.
So.
We're good.
So I was really interested in the fault tolerance that you talked about.
Yep.
So what happens when, okay, you have two props on each arm.
Correct.
I know you're doing that for more thrust, but was the fault tolerance part of that thinking
Yes.
originally? Okay.
Yeah, absolutely.
So when you have the big and the small, what happens when you lose the big, the top?
yeah. So
That's what happened.
That's what happened.
Three times.
Oh,
and-
you didn't have this big on the bottom?
No, yeah, so this,
Here.
yeah, so what, as we tested it, and again, we thought about leaving it as is. We wanted to test it to see what the problem was, so we rebuilt it to see if we could replicate it with different motors. So what we see here is this is the U5, so this is actually the full CAD. So this is exactly the CAD motor of a U5 Pro. This is exactly the CAD of this motor here. So yeah, the upper motor was 4 times the actual mass and produced only about 50% more, right, double the thrust, right? But yeah, so we actually had that 3 times. We actually had the upper motor, which again, these are 70% less efficient. If you look at the Pixhawk and what the output is, 70% of your throttle comes from the top 4.
Yeah.
30% comes from the bottom. So we lost an upper motor 3 times in flight, and the craft. And I wish we had more manpower in the lab, and we maybe have just a dedicated video camera operator. But the craft, when I say it didn't move, I mean it didn't. The attitude controller just compensated accordingly elsewhere.
Okay, I guess that's where I was going with this.
So the controller is tuned well enough,
Okay.
and the Pixhawk is smart enough
Right.
to compensate for all these things.
Otherwise, there has to be an explanation why it stayed that way.
Yeah, and those are it. Yeah, those are it. So
the
what
one below
we
is undersized, is smaller than the one on top.
correct.
Even though now it doesn't have a downwash to compete against it,
Right.
it's still powered less.
It's still powered less, and the Pixhawk is going to offset for that, right? It's going to recognize that even though, and again, right, there's no encoder, so it's not talking back. It's not saying, hey, I'm not spinning at
Right.
this
The
rate.
Pixhawk just knows that there's not enough thrust coming
From
this
this corner,
arm,
right.
and it increases the signal on both of those
So not enough
arrays.
thrust, or is there a?
Well, your IMU is telling you.
Your
Well,
IMU
it-
is
it
telling you that
sees
something's
the-
happening
yeah, it
here,
sees
so
the
it wants to accord, it
Yeah.
wants to
It
counteract
sees the pitch
and
roll
pitch
back.
it and pitch
Yeah,
it back. And what
to
you'll
be-
see, if you look at the log file, is you'll see the output PWMs reflect that, right? It'll still be outputting to the motor that's dead because it doesn't know anything about that, right?
It
So
just says
but what
send
you'll
faster.
right, just send faster. But what you'll see is the other motors will be a higher rate than you'd see in a traditional Tesla.
Yes, to be clear, it's PX4, not PX.
Yeah,
But
right, PX4,
the
right.
one that's dead goes to max, and then the one underneath it raises
Raises
above
up.
all the other bottom ones.
Right.
So is this something that current state-of-the-art systems are doing already?
Yeah,
Or
I
is
mean,
this something you fell into?
No, I mean,
Okay.
you get it for free when you deal with these flight controllers nowadays. These are all things that I think you get for free by
Okay.
taking things off the shelf and seeing how they can integrate into these packages. It's not something that we wrote in for this fault tolerance.
Yeah.
It's a nature of the platform. It's a nature of the design. Those kind of things.
And understanding how they work.
And yeah, right, the understanding of how these aerodynamics work. And I
Well-
think the biggest thing is this is our third iteration at something like this. So we built a much larger platform. We've discussed a little bit off topic tonight. But all of these started with thrust measurements. So with a thrust stand, again, I could have we could have filled slides, but we built a thrust stand on a linear actuator bearing on some, so we were able to actually test coaxial motors and see what thrust they actually produce combined. So that was the number, right? That metric was the number to have to say, hey, I can build this platform and I can know that I can have this all up weight and I can have this kind of a fault tolerance or this kind of an error issue and still be safe.
Yeah, and the
So that's
hardware
all that's-
integration isn't as easy as
Yeah, and I mean, right, it's
So-
taking all those things and then plugging them
Yeah.
together,
With-
like I was talking to
with
Kent
the
State a little bit,
firmware, yeah.
we've had failures before, right? So
Yeah.
one year to the date almost, we would have been here talking about, hey, this would have been really great if it just would have flown for another month. So it's, I mean, the integration of all these hardware things, once you check all the boxes, is still an undertaking.